All right, fellow robo-nerds, this is Mr. Gilbert. I'm going to record a few screencasts to try to get us started in Matlab function programming. So the version I'm running of Matlab is R2021A, but this should work in any version that's 2021A or newer. So if you've got the new 2021B, that should be fine. You also need to have already installed the BEST Robotics Playground in order to follow along with these tutorials. So open your Matlab and then go to your apps, click the down arrow, and then select Robotics Playground. Single clicks, please. Double clicks will open more than one. Once your app Playground is opened, you'll see that you have various getting started examples, and we're going to work on this obstacle environment first. For the game programming, you would probably be opening the BEST Robotics virtual game and then going to the autonomous programming template. But we're going to close that because I don't want to give you anything related to the game. So we're going to just do some general programming tutorials for you. So we're going to open this obstacle environment. Also notice that there's this nice bright green button for lessons. When you open that, it will open lots of different MATLAB lessons that you can go through, including an introduction to MATLAB, basic robotics movements, Simulink, robotics controls, distance sensors, and I'd highly encourage you to go through those lessons as well. So let's click on Obstacle Environment, and it will open our Simulink window. And I'm going to just maximize that a little bit here so we can see. I can close that in a minute. All right, so we now have, no, stop it, Windows. There we go, that'll work better. So we have a little simulator window. It looks a little bit different than your autonomous programming challenge, but you can still see that there's some left motor inputs, some right motor inputs, and then a variety of sensors. So we have a right distance sensor, a left distance sensor, and those don't exist in your environment for the autonomous programming challenge, but you do have a wheel encoder, and I think in the autonomous challenge you have a left and a right. But here we have some settings, so we're going to set this just to see what all of this stuff does. We're going to set these knobs. We're going to move them up here to, we're going to attempt to move those to like positive numbers, so let's go 53 and 53. I hate knobs on this program, by the way, and you're seeing why they're hard to control. And I'm going to hit run to start my simulation. I'm going to slide it over to the side so we can see our outputs. You see the robot starts to move. The left and the right got a positive value of about 53 each, and you can see that the encoder is just ticking away. It's kind of like the odometer to your car. And it doesn't matter if it's turning left or it's turning right. If I back up to a negative number here and back up to a negative number here, even though I'm going backwards, the encoder is still counting up. It's counting the number of ticks that the wheel has traveled, irregardless of the direction. So that's going to be kind of handy as we calculate our movement around this obstacle course. So in this obstacle course, my goal is going to be to move the robot in a square around this left obstacle. That's what my goal is going to be. So I want to move forward, I want to turn left, I want to turn left, I want to turn left, and I'd like to stop roughly in about the same spot. So I am going to delete all of this input, and I can delete the purple blocks. I don't need them. All I need is a left motor and a right motor. Now, I'm going to be using MATLAB functions. So when I click over here on the left in the white space, I want to go MATLAB, and I want to select function. It's going to bring up the MATLAB function block, and when it comes up initially, it's probably going to have one input and one output. But double-clicking into that function block will open my MATLAB coding window where I have the function keyword, the name of the letter assigned to the output, and the name of the letter assigned to the input. You can have as many inputs and outputs as you want. In this example, I want two inputs. I'm going to use the square bracket. That's the array notation in Matlab. So I'm going to have a motor for my left and an output to my right, and I'm going to close my bracket. Then for my inputs in this case, I only want one input, but I'm going to give it a better name than you. I'm going to call it encoder. Okay, and then I'm going to give myself lots of lines of code. I'm going to type the keyword end. That keyword end is going to end my function. So if I save it right now, you should see on the screen that it's going to change, and my Matlab function is going to have an encoder, it's going to have a left, and it's going to have a right. I can pull those over, the left to the left and the right to the right. Now I need this encoder to have some input, so I'm going to drag this arrow all the way around and attach it to the wire. So notice it's got the little circle. It means it's attached to that output, and it's going to come back in there every time. So the functions in Matlab, this is an electrical simulation environment. So the functions are being called constantly. So at the speed, the refresh speed of the program, the function is being initiated. It's going from the top to the bottom, and then it's starting over. So the whole function works like a giant infinite loop, and it runs until you actually hit the stop or something causes it to crash. So if I just come in here and I use that wheel encoder as my input and I test it, so my basic steps for any program is going to be read the input, process the data, and send the output. That's my 3 steps essentially in any programming algorithm, and Matlab is no different. So I want to read the input. So I want to say the encoder is my constant input. So if I store that as a value, okay, and then the semicolon is going to end that line. It's going to mask the input so that it doesn't show up. If I leave the semicolon out, it runs like a calculator, and it's going to output it down here at every stage, and I may want that at some point. Okay, and then I'm going to say, okay, process the data. So I'm going to do some checks here. So a comparison or a branching algorithm starts with the word if, and then in parentheses is the condition. So my condition, I'm going to say if my encoder is less than 500. And then I'm going to use good tabbing, even though it's not required or enforced, it's always a good idea. So if encoder is less than 500, then I want my left wheel to go forward, my right wheel to go 1 forward. That's 127 is the maximum forward direction for the left and the right motors. Negative 127 means backwards, and you can go any combination of integer values between those. So if my encoder is less than 500, then I want to go forward. Else, and notice it moves it all the way to the margin for me. Then my left is equal to 0, and my right is equal to 0. So I want to go forward for 500 wheel ticks, and then I want to stop. And then at the end of my if-else, I will use the end. Now I could actually combine this, and maybe I'll do that in a minute. But let's run this and see what it does. Don't be making fun of my error messages. You can't have a good code if it doesn't break 2 or 3 times. Okay. So let me stop that because that window was hidden. Restart. So I notice my encoder's going up. It gets to 500, and my robot should stop. And it looks like it's drifting, and my encoder is still going up, so I'm not sure what's going on with that. But my robot is not moving, so let me reset and play. I think that's just a little drift. When I stop powering, because of the momentum of the robot, it still continues to drift forward a little bit, so you'll notice some encoder drift until it actually comes to a complete rest, and that's just momentum in action. You can't stop on a dime. So that looks like I might have gone maybe a little too far, but I want to go ahead and turn right there. So let's test that. So if the encoder value is less than 500, then I want to go forward. Now I'm going to add a second condition. Now remember to stop your model. It won't let you make any changes. So if it's less than 500, then I want to go forward. Else if, all combined, encoder is less than 750, so that's another 250 ticks from where we stopped moving forward. Then I'm going to stop the left wheel, but I'm going to keep that right wheel powered at 127. By stopping the left and moving the right, it should execute a left turn. I could actually, if I wanted to turn even sharper, I could reverse that left wheel to negative 127 and do what we call a pivot turn. So let me save it, come over here to my window, and let's run it and see what happens. So in step 1, I'm moving forward till I get to an encoder of 500. Then for another 250, I am executing a left turn. But I noticed that that took me way too far. So I'm not doing the math on this based on my wheel size. Hopefully y'all are doing some math along with your planning. But I am just kind of experimenting here and trying to get this video made for you guys. So I know that 500 was good for the start, but my turn was way too much. So I'm going to back that down to 600. And then I'm going to save it. And I'm going to test it again. So we hit that 500 mark. We execute our turn. And I notice that 600 looks pretty good. It stopped me pretty close to where I wanted. So let's test the next stage. So the next stage is I want to try to go forward to get to the other side of this obstacle. So stop my model, and I'm going to add another else if. Else if encoder is less than. So it took me 500 to get from here to here. And I want to go not quite that far, so let's add like another 300 and see where that gets us. So 600 plus 300, my encoder gets up to 900. Then I want to go forward again, so that's left at full and right at full. Okay, and please exercise good coding conventions and use your tabs and spaces and good variable names, or else you make puppies cry. Run the model. We are going forward. And we're turning. And we're going. Oh, we didn't quite turn far enough and looks like we might crash. So we can adjust that turn a little bit and make sure we're going a little farther forward. So we need to add a few more ticks to this. So let's up that to 610 on the turn. And let's up this to 1,000. Save it and run it. Now, hopefully, again, if y'all are doing math on yours and you know your distances, that will take away some of your trial and error. That's a much better turn. Looks like we're got a better line. Okay, so we got almost all the way there. We'll add a little more. Let's go up to like 1,300 and see where that gets us. Okay, we need to go just a little bit further. Now I could be using my compass sensor in here as well, and the compass sensor will give us a heading, so I could do things like if compass sensor is less than 90 turn. But I've found that sometimes the compass sensors can be a little unreliable. We don't have a gyro sensor that measures our acceleration. That's good too, because we can tell if we're stopped or if we're moving, but that doesn't exist, and we also don't have a contact switch for this particular game. But that contact switch would be like a bump sensor on the front. You can see it right here on the robot. So if I actually I could tell it something like go forward until you hit the wall, until the contact switch is 1, and then turn left. But we're working strictly with this encoder value, so we need to go forward a little bit more. So let's go to 1450. And I think I turned just a little too much, so let's back that up a little bit and run the model. So step 1, move forward. Step 2, turn. Step 3, move forward until we get to here. Hey, that looks about right. We might end up having to go just a little bit further than that. So let's go ahead and make that up to 1475. Oh, stop your model. 1475, and then let's execute another left turn. So I know that last 90-degree left turn was about 108 wheel ticks. So I should be able to copy that math and come in here and say else if encoder is less than, and then 1475 plus 100 would be 1575 plus 8 would be 1582. Left 0, right 127. Oh, don't forget my equal sign. There we go. Run the model. Stage 1 or step 1, move forward. Step 2, turn left for 108 encoder ticks. Go forward for a lot of encoder ticks. Execute another left turn. Oh, we crashed into the wall, so we went forward a little too far. And it looks like we turned a little too far. So let's back that back down to 1455. And let's back this one down as well to 1550. So 1450 to 1550 is 100. It's a little less than that one, but let's give it a try. Whee! Okay, and we hit the wall again, so I need to shorten it a little bit further, and we overturned by just a hair, but that could have been related to hitting the wall as well. It's hard to tell. So let's back that down to 1440, and we'll need to bring this one down to 1440 plus 100 would be 1540, and let's bring it down 5 more from that, so 95. You know, like my background music, I don't have any, so I'm just gonna have to sing to you, and you'll just have to bear it. So we bounced off the wall again. So we are going too far still. So let's go 1400. And let's go to 1500 minus 5 would be 1490. Let's go minus 10, 1490. Save it. Run it. I apologize for the pause in the video. We had a little technical glitch there. All right, and we made that turn. That's good. We made that turn without hitting the wall, but I think if we continue along, we may hit it. So I'm going to back up even just a little bit more. Let's go down to 1390 and leave that turn alone. Save it and run it. Again, do the math. Don't do what I'm doing, which is troubleshooting when you'll spend too much time, but do the math. Use your wheel ticks. You know how many ticks there are per revolution. It's in the documentation for the game. You know how big the wheels are, so do the math. There we go. So I need to turn a little bit more and then proceed forward. And that time I did not hit the wall. So 1495. And then I want to go to the next stage. So I'm going to copy that else if block, Control C, Control V, fix that indentation. Actually, I want to fix all of this indentation since it's part of my function. I'm going to indent it all. There we go. That's better. Then 1495, and let's go another 600. Let's go to 2095 at a forward. Now, if I was commenting this like a good coder, I would come in here to each one of these and I would say, add my little percent, and I would say, this is step 1, go forward. Step 2, and I would really advise you comment if you get up to like a whole bunch of steps and it's hard, turn left. Step 3, go forward. Step 4, turn left. Step 5, go forward. Comments will really help the rest of your team kind of debug your code and work better together as well. So please use good commenting, good variable names. So go forward. Step 2, turn left. Step 3, go forward. Step 4, turn left again. Step 5, go forward. Oh, so I can see we're going to hit the wall there. That's a problem. So I need to back up to step 3. And the distance looks good on that, though. That's good. So the distance looks okay. It doesn't look like I need to adjust that very much, but I need to make that left turn just a little bit longer. So let's go to 1498. Save it and run it. I know it's a little tedious. We run, we test, we measure, we run, we test, we measure, we fix, we debug, we run, we test, and that's just the development process. You know, we come up with a solution and you test your solution and then you fix your solution and you test your fix, and it's a constant cycle. And that's the nature of engineering and software development, is run and test. So I'm still dragging the wall, so I still know I didn't turn enough, so I'm going to back up again. I'm going to go all the way up to 1500. Save and run. Turn left. That's a little better. Now I think I might hit the other wall. No, we're good. Oh. I think I almost hit the wall there, but it looks like... Nope, it looks like I did hit the wall there. So, turn just a little bit more. We're getting really close. I had to zoom in to really tell I hit the wall there. So 1502. Run. By the way, you can drag and resize these windows. I know a lot of times when I'm doing autonomous type coding, the top view is a little more helpful. So you can drag and resize, you can pull them out. There we go, now we're clear. So I can see that pixel of gray space. Boom. So I actually came back, I think, a little too far, but I can start my next left turn right there and still be okay, I think. So we'll stop it, and then we'll add else if the encoder is less than 2195. So the last one, 1502, 1390 to 1502, that's 1490. It's 112. So if we go to 110, it would be 2205 plus 2 is 2207. And this is step 6, turn left. Left equals 0, right equals 127. Run. Watch. Okay, now we're turning onto the crosswind. We're going to go past the runway. We're going to execute a 90-degree turn to the left onto the downwind. We now fly the downwind until we get past our runway, execute the left turn onto base. Oh, and looks like we clipped the wall just a little bit, but the turn angle looks pretty good. So fortunately, we're not really on an airplane, but we want to keep that 112 there, but we can back this up. So maybe just go to 2000 and make that one 2112. And let's run it and see if we correct it enough. Back on the downwind leg. Good. It cleared their own. Oh, we overturned a little bit. Hitting that wall really stopped our turn. So now we got off that wall. We know that we're overturning just a little bit. So let's just knock 2 off of that, and then let's see if we can go ahead and calculate our forward. And let's go 400. Let's go 400. No, how much should we go? Step 1, step 2, step 3. This should be the same distance as step 3, but in the other direction in theory. So step 3, we went from 608 to 1390. I'll use my handy dandy calculator. 1390 minus 608 was 782. So from 2110 to 782 should take us to 2892. 2890. And we want to go forward again. So let's see what that does. We're trying to end up right back in our starting spot right there. And around the obstacle. And let's see if we get back to our starting spot. Oh, it looks like we overturned a little bit too, but we got pretty dang close. All right. Stop. Run. Oh, we just need to go just a little bit further. We need to end up on this line, and we're up here on this line. So let's fix that turn. That turn left right here was a little bit too much still. We had a little too much turning left, so let's back it up again. 2108. Let's add a little bit to this. Let's try 2950. Run. So we follow that line. We turn left. And we follow this little column. And we're going to follow. We got a little bit of drift there, but we're not hitting anything, so it's okay. We come down. Oh, that's still a little bit to the left. But let's see if we get a little closer to the line. We can fix that a little bit to the left still. Oh, and that distance looks good. I think by the time we execute that final turn, and this time we're gonna try a stop, and we're gonna try a backwards turn when we reposition, since we're not gonna be moving again after that. So on the last turn, we'll do a pivot turn instead of a sweeping turn. So we need to fix this a little bit. Let's go 2105. And then let's add that to step 7. Oh, and fix my comment. That's not step 6. Step 7. Go forward. Step 8. That's a copy paste boo-boo. Pivot turn to home. And that one, instead of a 127 and 0, we're going to go with a... And we're not going to do that for very long. Let's just do that for 100 clicks. Let's go to 3050 and see what that looks like. So run that model. We're getting close. We're almost home. Yeah, now it's a much straighter line. Yeah, I like that one. We won't mess with that one. We're going to get there. Oh, there we go. Nice pivot turn. We do need to go just a little bit further because we're not quite to that center line for our home yet. So on step 7 to go forward, we're going to add another 10 to that encoder reading. And then we're going to say if it's less than 3050, but we needed to add some more to that. So let's go the 50, let's go to 3100. Run. So I do take requests for songs that I might whistle or hum during waiting times for any subsequent videos, so feel free to comment. And if you like this video, don't forget to like and subscribe to this channel. Wait, I don't have YouTube. Maybe I'll add this to my Twitch channel. I could say, I stream Matlab on Twitch. Yeah, don't be laughing, y'all judging. Whoa, I think I may have added a little too much to that one. So we're going to subtract a little bit from that pivot turn after we make a little bit longer leg. And actually we may not need to. If I add another 50 pixels to that, that's automatically going to subtract. So let's just run that last leg again. I wish we could fast forward. You can increase the time on the videos, but it doesn't actually, that's your playback speed for your recordings after you're done. So that speed slider, it's tempting and it looks like it should do something, and it does on the playback, but not on the live simulations. So it's set on 32x now. But it does not affect the live simulation. Again, that's only the playback speed. So we're almost to the center line. Hey, beautiful. We could stand to go just a little bit further, which may fix that overturn as well. So let's go 10 more. Let's go 15 more. Let's go to 75. The playback function is nice because you don't have to rerun the code every time if you want to simulate, if you want to like show your results. And in the case of the contest, you're going to have to submit your recordings. So it really does help you do some troubleshooting if you need to say, well, did I actually hit that wall? You can change your views up here and then rerun your playback at different speeds, and you can test things like, did I hit something or did I get to my destination? So we're going to get to that center line and boop, and we're going to turn, and that's beautiful. We're going to reduce that turn just a little bit. So you see the difference between the pivot turn and the sweeping turn. The pivot turn executes a lot faster, so from 975 to 3100 is only 25 wheel ticks, but we turned 90 degrees where it was taking us 112 wheel ticks to do the sweeping left turn. So we can actually back that down just a little bit and go 30. 90. And then I think we need to go forward just a hair, but I think we actually may be really close to this spot. So the cursor is right where we should end up. Hey, we're going to call that one good enough. Alright, so that's going to conclude this video. We're going to stop the simulation. Again, we'll review this code one more time. So your function has two outputs, your left and your right. Those outputs must have values at all times, or you'll get an error message in Matlab saying that your outputs were undefined on certain branches of your code. And that's what this else is accomplishing right here. It's making sure that when we're done, if every test fails, that left and that right still have a value. Another technique to do that is at the beginning. And then this part, we ended up not using that at all. So we could delete that as well. So again, use good variable names, comment your code, test it, run, and run often. All right, good luck.